So now we're going to look at some more advanced filters where we look at orientation analysis, looking at misorientation between adjacent grains, internal misorientation in 3D, and also how we put a surface mesh on the grains, and we can start to extract some grain boundary parameters as well. So in your folder there is an advanced pipeline, but don't cheat. I think let's try and build it. I think if we build it ourselves, that's good. And obviously this isn't perfect either, so I think but this is just to give you a general framework of what kind of stuff you can do once you've got a nice 3D data set which you're happy with. Where's the mouse? So again, this is a really good thing about doing 3D. Once you've got a nice data set you're happy with, obviously you don't have to run through that basic pipeline every time. That's a really important thing to note, that once you've got a Dream 3D file which you're happy with in terms of the 3D data and the general alignment and cleaning of it, that's then there, and you can then read that in as many times as you want, do more and more filters on it and write that out. So you don't have to repeat that basic pipeline as long as you're happy with it. So once you've got a data set you're happy with, you can use this filter read Dream 3D data file, and that will read in your .Dream 3D back into Dream 3D, and then you can do a load of other stuff with it. So again, you'll see your standard data structure when you read it in. So all of your cell data and your feature data and your ensemble data are all there. Again, if you're really worried you've got a 30, 40 gig data set at this stage, and you want to cut it down, and you know you're not going to use some of these attribute matrices, you can untick them and get rid of them to reduce your data size. And you can do that anytime you read it in, but be careful, because once you get rid of them and you do an action on it, and then you write this Dream 3D data file, they're gone then in that subsequent data file. So make sure you won't need them again in the future. So yeah, read Dream 3D data file, that writes it in. And then the first one we're doing here is find feature average orientation. In itself, it's not that useful. So what this will do is it'll take all the Euler angles for each feature and calculate an average of that, and it will give you a single Euler angles, 3 Euler angles for each feature. So you'll see it here. So on the feature level, we get average quaternions and average Euler angles for each feature. Again, not that useful in itself, but this is useful for some subsequent filters we're doing. But now you'll see you're creating 2 new objects, which are, for each feature, you now have your average orientation in both quaternions and Euler angles. Find feature neighbours. This is a pretty cool one. So this determines the number of grains each feature is in contact with, and we'll actually write the feature IDs of those grains as well. So this is really important. So you will get number of neighbours list, which will tell you for each feature how many neighbours it has, and then neighbour list will tell you in order what those neighbours are in terms of the feature ID. So now you will know not only you'll know how many neighbours each grain has, and also what the feature IDs of those neighbours are. So then you can go back and say, right, is that grain next to that grain? If it is, then you can start to calculate misorientation across that boundary. And then you also get this shared surface area, which I haven't really used, but that tells you how many elements are shared across that boundary. So that's basically your grain boundary area of that particular misorientation. I've never really used that, but it might come up later on. Any questions on that one? Okay, so once you've done that, we can then find the misorientation of these features. So if you look, this is the filter find feature neighbour misorientations. You can see it takes your neighbour list and your orientations and your crystal structures, and calculates your misorientation and your average misorientation. So your misorientation list is a list of all the misorientation angles between that feature and all the neighbouring features. And then you can plot it. I plotted this just using HDF view, just extracted the data as we did with the size data, and you can plot your misorientation angle distribution, which is quite powerful. This important thing is that this is only plotting the angle, not the axis, but it does have the important thing is you do have the orientation of each of your neighbouring grains. So if you would then want to do some post Dream 3D analysis to properly analyse that boundary, you do have the orientation data of each grain as well. But this is just the misorientation, which is a simplified view of the grain boundary. It also does the average misorientation, which I don't really know if that's very useful. So that's the average misorientation angle between that feature and all the surrounding features. Don't know if that's useful. I don't think so. But if you're not interested in that, you can just uncheck that box. But what we're really interested in is this misorientation between the that grain and all the adjacent grains. Next one is CAM. Now you need to be careful with this, because even on this small data set, this might take a long time. So this plots your misorientation between each kernel, defined as whatever your kernel radius is here. So I've got 2 by 2 by 2 voxels, and it will calculate the misorientation of that kernel in relation to all the surrounding kernels in 3D, and it will write the average of all that misorientation to the central kernel. It's exactly the same as you do in a CAM map in 2D, but in 3D basically. And you can end up, this is just an example of a CAM map which is really useful for us from the oxidized zirconium alloy, and we can now see this this band of misorientation on the oxidized surface, which is a result of the metal trying to constrain the volume expansion during oxidation. And when we look at this top down, we see some really interesting features in the CAM map which show that the levels of misorientation in this oxidized surface are dependent on the underlying metal grain orientation. And we also get some interesting localized regions of high deformation as a result of particular grain boundary types as well. So some really interesting stuff we pulled out there. You might want to be careful when you're running this. I don't know how quick it'll be on these PCs, but on my laptop this can take hours, depending on the size of your data set obviously and what your kernel radius is. But yeah, you might want to be careful using this, because obviously it's going every voxel to voxel for your entire data set, and it can take a long time. So if you want to look at our intragranular misorientation referenced internally within the grain, we can do a find feature reference misorientation. So this will determine the misorientation within a particular feature or grain in relation to another point in that grain. So generally we use a reference orientation as the average orientation of that grain. So that's where that first filter comes in, of finding the average orientation. And this will show you the orientation of every voxel within that feature in relation to the average orientation of that feature, which can be useful for looking at intragranular misorientation. Here's an example of a single grain pulled out from that zirconium data set, and this is the feature reference misorientation for that. So it's another way of looking at orientation in relation to a reference point. And I think the other option, and with reference orientation, you can take the central point of that grain as well, instead of the average orientation, and that'll be the center of mass of that grain, the orientation of that voxel, which can show you how the orientation spread differs as you go towards your grain boundary. Oh, hold on. Right, so one of the issues we have, I'm just going to flip back to Paraview here. So just for visualizing grains, and if you want to then, plot a grain in a paper with a more accurate grain shape, you can, so this is an example from our basic pipeline. We can start to see we have very voxelated data, and this becomes more apparent when you look at smaller grains. So what we want to do now is put a surface mesh onto this grain surface. So for this, and this is important, this isn't just a visual thing, this isn't just to make it look nicer, this is really important when we start to calculate properties of grain boundaries. Because obviously if we start to look at the grain boundary plane here, it's going to be changing by 90 degrees every voxel, and it's going to be nonsense. So what we want to do is apply a surface mesh to this voxelated data, and then apply a smoothing algorithm, which will then give us an actual proper representation of the original grain boundary, which is very useful for calculating the grain boundary energy for stuff like stress corrosion cracking and anything really. So if we go back to the pipeline, We do this with this filter called Quick Surface Mesh. So I'll go back to presentation, sorry, not the pipeline. So yes, this applies this triangular data structure onto our voxelated surface here. So you can see it basically splits our data up into these triangles. And now, crucially, we have a whole new data attribute array now with these triangle datas in them. And each of these, it saves as node, vertex data, and face labels. So each of these triangles now has a unique identifier. So similar to the feature IDs, we now have face labels, which identifies each of these triangular triangular regions as a individual face. So yeah, that's the surface mesh, and each of these points in this is a node as well. So this is where it gets a bit complicated. When we come to look at this in HDF view, you'll see that it's now a bit more difficult to visualize when you start to think about the HDF5 file. But this schematic kind of helps. So all you've done is you've split your voxelated data into a surface of triangles, basically. And each of those triangles has properties.
What sort of data would you select to move over to the minute it's unavailable, not selected?
So all that's doing is, that's just, you basically copy everything over, but your size of your data becomes an issue. So you'd only copy. So this is, anything you then want to view on your mesh data set from your cell data, you'd have to copy across here. But yeah, I think in an ideal world, you just copy across everything, then you've got it for later. But if your data set's 30, 40 gig already, you probably only want to copy across stuff you're actually going to need. So IPF color would definitely be one. You wouldn't want your Euler angles. Feature IDs, you'd probably copy across because then you can color your grains according to unique IDs. But yeah, that's a good point. You want to copy across anything from your cell level data, which you will then want to color your mesh in with. And here's an example of a surface mesh onto a voxelated data onto surface mesh. You'll see it doesn't look any different. That's not surprising because it's just a meshed surface on your voxelated data. But now, because we now have this surface mesh with this triangular structure, we can now do a smoothing function, which is called, don't ask me why, Laplacian smoothing. And what this will do is don't ask me what all these parameters mean, I've only ever really used the defaults. I have increased I increased the iteration steps quite a bit. I found that you hit a minima pretty quickly on this kind of grain structure, but you might want to play with these for your particular grains, particularly if you have some very sort of weird grain structures that don't have smooth surfaces. You need to be probably careful with how many iterations you do. But I think I used 1,000 iteration steps when I did it for this data set. But yeah, I think you can play around with these parameters. I really haven't. I just generally use the defaults. And if you click, I should have pointed out actually, any filter, if you right click, you can go to filter help and it'll open up a web browser and it'll explain what the actual algorithm's doing. So if you're interested in that, you can dig in and see what each of these parameters is doing. But generally, you end up going from this kind of structure with the voxelated data to this kind of really nice smooth structure, which much more closely represents our original grain structure, we hope. So this is probably not that relevant for today, but for future work, if we want to then calculate properties of our grain boundary in terms of grain boundary plane and our 5-parameter grain boundary distribution, we then want to generate some statistics on these triangles themselves. So here we can get the area of each face, we can get the centroid, which is the central point of that face, and we can get the normal of that face. And the normal of that face is very important for calculating the grain boundary plane, which is what really determines the grain boundary energy, so really important. So this is 3 filters which extract properties on the orientation of each face face region. Then once we've got that, we can do some cool stuff like generate misorientation colors. This is just examples, by the way. You can do loads of other stuff. This is just some examples I pulled out on what you can do once you have this mesh data with all the parameters for each triangle. You can then plot the misorientation, which is the example I showed right at the start. So this is that single recrystallized Zerk grain, colored, each boundary colored according to the misorientation with the adjacent grain. So you can see here it's taking our face labels, our orientations of each feature, crystal structure, and it's calculating the misorientation for each boundary, and then we're colouring that onto the mesh. I think I've got another example. This is where it gets a bit mental. So now we've got the orientation of the normal direction of each segment of the surface mesh. We can then plot that in IPF colouring, which is using the reference direction as that normal. And this basically shows you how much the grain boundary plane changes across a particular boundary. And it's also showing up some artifacts in the data slicing as well quite nicely. So you can see these regular structures. But yeah, this is just an example of, at the start when I said, you got this really nice recrystallized microstructure, and and even at this stage you start to think, let's go back a slide. At this stage you start to think, oh yeah, I've got an idea of what's going on here. Each one of these is a particular grain boundary misorientation. Yeah, okay, I can kind of deal with that. And then you go another stage and you realize how much that grain boundary plane is changing even on a single misorientation angle axis pair. This is when you start to realize that, hold on, grain boundaries are pretty crazy. And and you can't just go from a lot of papers, try to correlate things to a single misorientation value from a 2D EBSD. You can see that doesn't mean anything really. And in terms of stress corrosion cracking and grain boundary energy, you can see that even on a particular single grain boundary, your local atomic ordering is going to change massively. So you need to really consider this when you're looking at crack propagation or corrosion, anything like that involves the grain boundaries. Yeah.
I think there must be, generally you can see there's a red-ish boundary,
yeah,
a greenish boundary, and sort of bluish-greenish. And that is also the variation in colour could come from your slices.
Yes, so there's definitely some artifact.
Mesh could not be perfect.
100%. I think there's an important thing here with this. This is showing up some artifact of the slicing and the fact that when we reconstruct in that Z direction, we're not getting a perfect alignment.
Yes.
Definitely.
There's something to
yeah, 100%. And that's good for Jacopo, I think, for when we're looking at trying to improve the alignment between Z slices. This really shows it up quite nicely. We see this systematic shift in the IPF colouring. But yeah, that takes a while for you to get your head around what that colour's actually showing. But it's IPF colouring, but your reference direction is your grain boundary normal. These aren't in. Yes.
It's not around each grain as you're showing, is it? It's the boundaries that are being meshed, and then it's putting together for that image.
This image, yes. So it's yes.
So because if you meshed each grain, they might not necessarily stick together.
Yes. So it's a boundary.
So these are.
Yeah. So we'll show when I show the visualization next. Each grain boundary will have two feature. Each mesh segment will have two feature IDs associated with it. One will be grain on each side. These aren't in the example filter, but this is just some stuff I did on some older data. So there's a filter called Find CSL Boundaries. So coincidence site lattice is a notation we use for looking at particular specific types of grain boundary. So twin boundaries, for example, where you have lots of coherent lattice sites. This is just an example for in Zerk dataset. You can start to pull out particular types of grain boundary, which is pretty cool. I think these were CSL9 boundaries. And then if you really want to confuse yourself, you can start to look at grain boundary GBCD pole figures, which is, to be honest, a full description of a grain boundary type. And what you're looking at is for a particular angle axis pair, this is the variation of grain boundary plane in that reference frame of that angle axis misorientation. So this is a full description of that grain boundary type, which you can't get from any other, well, not any other method. You can't get from 2D methods. So really powerful way of looking at the actual description of a grain boundary, which you could never ever get from 2D analysis. I've got some papers on GBCDs, they'll kind of blow your mind a bit, trying to get your head around them. Very difficult to visualize, but yeah. But yeah, if you want to talk to me about GBCDs, I'm happy to talk about it. Interestingly, the guy who wrote it, the original papers on GBCDs from like the 70s or 80s were written by a guy called Greg Rohrer, who I went to visit over in Pittsburgh, and he wrote the original code on Fortran with input cards, punch cards, and he fed them into a machine, and then he'd wait all weekend, and he'd go in on Monday morning and get his outputs, and that's how he was describing grain boundaries with Fortran punch cards. But mental. Right, I think this is the last slide on this bit. So now we can use HDF view again to now look at the data structure once we've run a more advanced pipeline. Again, we see a lot of the same stuff we saw before in the cell data. We have a bit more data in our feature data, such as our average orientation data we calculated before. But very crucially, we now have a whole new data container, which is our mesh. So a triangle data container, which is all of our mesh data. So now if we ever wanted to go in and properly calculate our grain boundary planes and everything, that's how we do it with this triangle data container. So once we create our mesh, we get a whole new data container. So you end up with 3 data containers, basically your cell data, your feature data, and your triangle data. Before I let you loose on your own data, I just want to show you how we would go about visualizing a meshed data set with Paraview. Because it's a bit different. So I'm just going to load up the one I made earlier, cropped mesh. Again, XMF reader 1. Again, same procedure, apply. Oh. So now it looks mental because this is all of our triangular segments of even our non-index data. So again, we can just do it as we did before. We want to. Now you will notice in your drop-down menu, you now have a number of other possible scalar quantities you can threshold against. Now you'll see in brackets partial after each one, and that means that it's not the entire data set, because now we have this extra triangle data container. Now we can threshold only on a certain subset of the data. So just to simplify that a bit, if we go mask partial, exactly the same procedure as before. I need the keyboard. 1, apply. Again, this should be quicker with your machines, hopefully. Uh-oh. It's coming. Right, so this is exactly the same as before. Because it's a partial mask, it's only applied it onto the cell data, and we can just get back to exactly what we had before with the mask. Now, say if, what was the grain we had before? So if you want to pull out a particular grain now, but with a mesh, what was this feature ID? 164, so that was our grain before we had 164, this voxelated guy. So now if we want to see him with a smooth surface mesh, we'll go back to here, threshold. And now, you know, you asked Jack about the boundary, and so each face, each triangular mesh segment will have 2 feature IDs associated with it, 1 grain on each side. So there'll be 2 different feature IDs for each mesh segment. They're saved into different attribute arrays called feature 0, feature 1. So if we go, what was it, 164? Yeah, 164. First of all, if we do face labels, so the face label is the feature ID on one side of the boundary. If we do 164 there, 164, apply. That will bring up all the face labels with a 164 on one side of it. So we should get, Okay, so that's a nice grain boundary segment. It doesn't look very smooth, and that is probably because in my example pipeline, I didn't iterate, I only iterated once because I was rushing yesterday. So it kind of looks, because we've only done one iteration, it's basically voxelated. So if we go back to here, smoothing, there's only one iteration step, so it's basically, we haven't done any smoothing. So that's why it looks like that. So that's something for you to play with. But now you can see we haven't got the entire grain surface. That's because there's some other face labels in there where 164 was on the other side of the boundary. So then if we go again, threshold, feature 1, which is because I think it's basically similar to how your feature IDs are assigned randomly. Your feature ID on each side of the boundary will just be randomly assigned. So some of them are feature 1, some of them are feature 0. So if we go 164, 164, hopefully this works. It should fill in the rest of the grain, which are all the other face labels with a 164 on the other side. And sadly, because I only didn't do any smoothing, it looks identical. But yeah, so that's how you would visualize a grain in on the surface mesh. But hopefully if you've done some smoothing, it will look much nicer. And then you can do any of your coloring which you've applied to your mesh, you can then color. So we did IPF coloring. So we want feature 1, feature 0. And yeah, that's it. It's as simple as that. So yeah, I reckon take your initial data set and yeah,